All right, well, this time, what are we looking at? We're looking at variadic functions this time around. So last time around we looked at macros in C and C++, so the hash-defined side of things and the template programming side of things. This time around we're actually going to try applying it to create functions that can accept any number of arguments. So you've already used things like this in C with functions like printf, where the first parameter is the format string and then there can be any number of additional parameters. So they exist in C, it's just a question of how to make it work. And similarly, we can come up with them in C++, and actually with the use of templates we can get some fairly interesting ones in C++. But we'll take a look at how to get this up and running. So in the C version, we're going to use a library called stdarg.h, and in the C++ version we'll use templated functions. All right, so if we're thinking about how this stuff works behind the scenes, if you think in terms of the runtime stack, then the parameters for a function are going to be sitting at the top of the stack frame usually. So if we've got a variadic function, one of the ways the compiler could deal with it is to simply throw an extra parameter up at the very top that says there are, on this particular call, there's 15 more parameters coming, or on this particular call, there's 7 more parameters coming. So that way the compiler can very easily add information that the function can then use to process the correct number of parameters. All right, so let's take a look at how we can make this work in C. And again, we're going to use this stdarg library that declares a whole bunch of macros that are used to actually go through and do the dirty work for us. So we're simply going to make use of those macros from stdarg.h. So the syntax for declaring the function is you give a count, or an integer variable that will hold the count of the number of additional parameters that are passed. So effectively that thing that the compiler would have pushed on the top of the stack. And then the dot 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 as the actual syntax to indicate any number of parameters could come after this. So when we actually go to call the function, so if we actually go to call f in this case, we'd call f and we'd pass a count first of how many more parameters are coming up. So I'm going to say there's 3 more parameters coming up after this one and pass the 3 parameters. So you do always have to make sure that you've got that first count right for the number of additional parameters that are coming out there. Now, in the function implementation, so in our function f in this case, again, we're going to make use of a bunch of macros that were set up for us in that stdarg. So one of them is va_list, va_list, and that's going to actually have the list of additional arguments that were passed. va_start goes through and sets up the list for us and initializes it essentially sets up the storage for the list somewhere off in memory based on how many arguments we're expecting to be passed. So we tell it how many we're expecting and we call va_start. Right? va_list sets up our argument list. va_start initializes it based on the count of how many we were expecting. Then we're going to go through and use the arguments, and we'll talk about that in just a sec. And then at the end, we'll clean up the storage that start allocated. So va_end cleans up the all of the stuff that start allocated probably somewhere off on the heap. Now to actually use it, there's yet another one called va_arg, where we give it the argument list and the data type of the next thing that we're expecting. And it goes through and grabs that as the kind of next thing off the stack frame, or the space that it's set up in the storage, and returns it for us. So we store that in a variable of the appropriate data type. So if I'm expecting the next thing to be a double, then I'll store it in a double, for instance. Right, so this goes through and grabs the next one. So all I'm going to do is keep track of how many times I've run va_arg and how big n is. And so I'll go through and make sure I grab all n of these and do whatever it is I'm going to do with those n arguments. Now they don't all have to be of the same data type, but as I'm going through running va_arg, each time I call it, I have to know the right data type for the next thing I'm expecting. So I have to know in the function what data types I'm expecting in what order. Now, the way something like printf would do that is it gets that first parameter, the format string, and it reads through the characters in that and looks for the %fs and %ds and that kind of thing to tell it what kind of argument it should be expecting next, and based on that, it supplies the correct data type for something like Varg. So you can go through and do this. Now, what we'll do is just run through a complete example of this just to give a kind of a feel for the whole thing. So it's not ideal, especially due to the typecasting, and actually there's some limitations as well. There's kind of a limited set of data types that it will accept here. You can't just throw anything in. You're safe with doubles and longs, but you have to be a little bit careful with the data types outside that. So it is kind of limited. But let's have a bit of a play with some of our examples here. So let's, I can't type. Yep. All right, so here's the C version. And again, we've got our function sum that's just going to take the sum, and I'm going to expect that all of the arguments are longs for this time around. So again, we have a counter up front for how many more arguments we're expecting, the ... to indicate that there can be a whole bunch of these things coming, the VA list, and whatever your variable name is to initialize your list of arguments from the ... the VA start to actually set up the storage for it based on how many arguments it's expecting, and way down at the end here, the VA end to clean that space up. And then in here, I'm just going to use I to keep a count of how many of the arguments I've grabbed so far. So I'm going to start it at 1, I'm going to keep going, go through and I'll grab the first one. So grab it from the argument list, I'm expecting it to be a long, and I'm just going to store it in current. So each time I go through, I'm going to store it in current, and all I'm going to do is take the sum here. So I'm going to have a running total that I'll also initialize from current. So while we're not done, while there's still arguments out there, right, while I is still less than n, we'll go through, grab the next one, add it to total, bump up our counter, and just keep cycling through. So again, this is a nice straightforward example, but it works fairly well. So we go through at the end and clean up our storage, and then return that total that we worked out. And so just a few examples of different calls here. We'll call it once with a single argument 10. We'll call it a second time with 2 arguments, 1001. Call it another time with 5 arguments, 120, 34, or 300, 4,000, 50,000, something like that. And we'll just print out the results. So let's compile the beastie here. And try running it, and hopefully it gives us the right totals. Right, so it goes through, grabs the 10, the 1001, the 54,321. So we do get the behavior that we wanted. And again, it's not horribly ugly to go through. It's not pretty, but it works, and we can create these variadic functions now. All right, so that was the C approach using macros. The C++ approach is going to be to use these template functions. So what we're going to do for this is, for our variadic function, we're going to need one that accepts just the base number of arguments, the minimum number of arguments that you're expecting. So this is the base case version of the function. So for that sum function that we just did, maybe the base case is it expects a single parameter. And then we're going to write a second version of the function, and they're each going to be templated. And this one is going to take a fixed number of parameters at the front, so maybe just 1 at the front, and then any number of additional arguments. And it's going to make a recursive call on the additional arguments, and then process the one fixed one at the front. And so essentially it's peeling off one argument at a time from the front of the list and doing a recursive call. So in this case, with the C++ version, we don't have to provide a count up front. We just provide the collection of arguments that we want. And again, what I'm going to do is come up with a sum function here, same idea as we did with the C one, and we'll write one templated version that expects one parameter exactly, and one that expects 1 plus an additional collection of parameters. So the syntax for the basic one, if we're just doing a sum, Again, this is a templated function, so we specify what we want to use for the type name. And for this, all the sum is going to do is, well, the sum of a single argument is just whatever its value is. So this is fine. Whatever data type x is what we're going to return, and we'll simply return x. So nice and easy. For the recursive one, what we're going to do is return a required front argument plus a recursive call on all of the rest of them. So this is where the syntax for the templating gets a little weird. We supply the type for that first parameter, and then our ... type name for the subsequent collection of one or more arguments. And we give a name for that list of additional arguments that's going to come up. And when we do our recursive call, we say, okay, I want to call recursively on that list and the ... So now we've got 3 places where the ... is cropping up, right? Our type name, our args as our formal parameter type, and our args as the actual parameter that gets passed. And again, you want to be careful which names you're using, right? This one is the type name with the ... This one is the actual parameter name. So as long as you're okay with that, right, it's just getting these 3 beasties correct, then you can set this up. And again, you can do the recursive call on the rest of the things and then do something with x afterwards, or do something with x and do the recursive call, whatever happens to work out. But you can go through and set up this recursive process. So again, it's templated, so it's more flexible with respect to the data types. You just have to make sure that whatever data types you're actually using here, so whatever t is, had better be compatible with whatever operator it is you're using in this. But other than that, it's a fair bit more flexible. You can throw in, you can have a bunch of required arguments up front, and then whatever is additional, so you could peel off 2 at a time, or 3 at a time, or 4 at a time, and then just say whatever's left after that. So there are a variety of different things you can do with the structure, but it does let you play with it. So let's just make sure we can get that working on the C++ side of things. So again, same basic idea. We're doing a sum of just a whole bunch of longs. Again, the data types could be strings or doubles or anything that the plus operator works with. So in this case, we provide our base case version, where if you just give me one value, I'm just going to return it. And if you give me more than one value, the first one goes into x, and the rest of them goes into this arguments list. And so I'll take the sum of x and a recursive call on the rest of them. And then again, we can try it out with the same idea. We'll call it with 1, we'll call it with 2, we'll call it with 5, and hopefully it gives us the right results here. And cross your fingers. Yeah, that looks about right. So we can go through and set up now variadic functions in either C or C++. And again, the structure of it looks quite different. And again, you can compare and contrast this with the idea that we saw of using the and rest in Lisp for setting up variadic functions. And you get a feel for some of the different ways that different languages approach the problem. All right, I think that's probably a good place to leave this one.